Hello, everybody. Welcome to the second event today. This is going to be our second workshop, and we're going to be talking about LatticeFold, a lattice-based folding scheme and its applications to succinct proof systems. We have Boneh joining us in a second, coming to the stage. As we kick off the workshop, please be sure to say hi in the chat section. We're really happy to have you again for the second workshop today. For those of you thinking what's happening with the previous workshop, for those of you that missed it, we will make sure to have a recording ready and available in the next 24 hours, which will be exported and added to the Hacker Pack. So if in case there's any question, GM, nice to see how many inactive you are here. Fantastic. Dan, you should be seeing a pop-up on your end. Please let me know if there are any issues.
Here.
Fantastic. Welcome on stage.
And you want me to share the screen?
Perfect. Yes. Feel free to do a quick intro, introduce yourself, and maybe take it away.
Oh, okay. How many people are here?
Quite a lot, based on how active the chat is. Even I don't know. We'll have to look at after the event of like the exact numbers.
Oh, excellent, excellent. Well, welcome everybody. Let me share my screen and we can get started.
For anybody that has questions, please make sure to post them in the questions tab on the bottom right side, and then we'll be able to go back to them afterwards or during the talk based on as he sees fit. So yeah, Dan, over to you.
Okay. I'm trying to join over on my iPad, but for some reason it's
sure.
not me, but I don't know. It just keeps on asking me to join. But anyhow, I don't know. Maybe I won't use the iPad then.
As I said, I will be asking everybody to post their questions in the dedicated questions tab section. So if you want or take a break every now and then to see if there's anything pressing, feel free. Or if you want, you can do it at the very end.
Actually, it's perfectly fine with me if you stop me. If there's interesting questions, please stop me. I like to make things interactive. So if questions come in, I might as well take them on.
Sounds good.
Yeah, maybe I'll try to make it like 45 minutes and leave time for questions at the end. Yeah, does that work?
Sounds good. That would be amazing. I'll be off stage, but we'll pop on in case anything comes up.
Okay. All right. Yeah, so this iPad thing is not working. Okay, well, welcome everyone. Let me just hide this thing. I hope you can you all, whoops, what just happened? Can you all see my screen?
Yes, we can see and hear clearly.
Oh, perfect. Okay, so in that case, let's get started. Okay, so welcome everyone. So I was asked to give a talk actually with very, very little information about what the audience knows and doesn't know. So I decided to play it safe and start from the basics. And so maybe I'll go through the basics quickly, and then we'll get to LatticeFold. Again, I have no idea what everybody's backgrounds are. So I'm going to talk about, the main thing I want to talk about is a work called LatticeFold, which is lattice-based SNARK folding scheme. This is a joint work with Boneh Chen. It's available on ePrint if you want to read more about this. Yeah, happy to take any questions. So, but like I said, I don't really know what everybody's backgrounds are, so I decided to play it safe. And so let's just start with the basics, like what is a SNARK? So when I have to explain what a SNARK is to a general audience, I say that it's basically a succinct proof that well, it's a succinct non-interactive argument of knowledge. That's what the letters stand for. But really, it's a succinct proof that some certain statement is true. For example, maybe I can give you a proof that I know some message M whose hash happens to be 0. The interesting thing about SNARKs is that the proof has to be very short and it has to be very fast to verify. And just as one example, like if the message that I know happens to be really big, let's say it's a gigabyte long message, then the trivial proof where I just send you the message in the clear as my proof, that's not a SNARK, because now the message is the proof would be a gigabyte long, and you would have to hash a gigabyte of data in order to verify that it really hashes to 0. Yeah, so the goal is to basically have SNARKs that are super short, say under a kilobyte, and the time to verify them would be in the milliseconds, sort of independent of how big the witness is. We also have ZK SNARKs where the proof itself is supposed to reveal nothing about the message M. Both SNARKs and ZK SNARKs are really interesting and have lots of applications. And we'll talk about that in a second. So again, I'm not sure what everybody's backgrounds are. I just wanted to make sure everybody understands the syntax here. So the easiest way to explain this is that we fix what's called an arithmetic circuit. So we fix a finite field. So numbers 0 to p-1 with addition and multiplication modulo p. We fix an arithmetic circuit over the finite field. The circuit takes a public input called a statement x, and it takes a secret witness w. And the prover is trying to prove that given x, it knows a w such that the circuit evaluates to 0. So c of xw is equal to 0. And the way we do that is basically we use what's called a pre-processing SNARK, where we apply a setup algorithm to the circuit that generates prover keys and verifier keys. Then we give the prover key to the prover, we give the verifier key to the verifier. And you notice the prover has both the statement and the witness. The verifier only has the statement and the proof. And then it's supposed to say whether it accepts or rejects the proof. So the point is, the verifier should only accept the proof if it really believes that the prover has a witness W that makes the circuit evaluate to 0. And we said that the SNARK is succinct if the proof is short, and the time to verify the proof is also very short as a function of the size of the circuit. Okay, so again, I'm going to go through this really quickly. SNARKs have to satisfy these standard properties. Completeness means that if the prover is honest, it will honestly then the verifier will accept the proof. Soundness means if the prover is dishonest, it's going to fool the verifier with only very low probability. Knowledge soundness means that if the verifier accepts, that means the prover actually knows a witness for the instance X. I'm not going to define that formally. I just wrote that over here very, very informally. It just says if the verifier accepts, the prover knows such a witness. And like I said, the important property is succinctness, that the proof is short, and the time to verify the proof is also very short. Okay, so that's kind of a quick summary of what SNARKs are. If you think about it for a minute, you realize, I can prove to you, again, that I have a gigabyte message that hashes to 0. The proof is going to be like under a kilobyte, and the time to verify it is going to be also in the milliseconds. It sounds impossible. How can I possibly prove to you that I know such a message with such a short proof? But it turns out, magically, this is exactly what SNARKs let us do. So the breakthrough that's made SNARKs all of a sudden all the rage, why everybody's interested in SNARKs, is first of all, we have really good provers now. So proof generation is either linear or almost linear. But beyond just being linear, the provers are just fast. Yeah. So in terms of the size of the computation, we can actually prove quite large statements these days. I guess the numbers, if you want concrete numbers, like if we want to prove like a RISC-V computation, it's really quite remarkable that just on a few GPUs, companies out there are able now to prove like several tens of millions of instructions a second, which is really quite remarkable. This took many beautiful ideas to get to this point. Like really, this is a pretty large area, lots of beautiful ideas in it. And of course, there are lots of commercial applications. Maybe I'll mention, I kind of fell in love with this area a while ago. And this area has such a collection of beautiful ideas that actually this spring, I decided to just devote an entire quarter just to develop to a course just on SNARKs. So this spring, I'm going to be teaching a course at Stanford just on SNARKs. We'll make all the materials available online, so if people are interested, they can follow along. Should be a really, really fun course. I'm going to kind of focus both on the applications of SNARKs and all the techniques, or many of the techniques that go into building these efficient SNARKs. Yeah, so the point of SNARKs is if I give you a short proof that something is true, you don't have to verify that statement over and over again. It's sufficient to just verify the proof. This is why these things are so useful on the blockchain. We don't need all the validators to validate a whole bunch of transactions. All they need to do is just verify a proof that says these transactions are valid. So we kind of eliminate repeated computations, repeated checking by just reducing it to just checking a proof. And of course, a ZK SNARK is an important tool for privacy, and I'll give examples of that in just a second. So yeah, so I kind of listed. I stole this from ZKV. It's amazing to me how many companies are working in the SNARK space now. As you probably all know, this is a very active area, both active area of research, but also an active area commercially, where there are lots of companies that are either deploying new SNARKs or deploying applications of SNARKs. Generally, I would say if you're new to this area, one of the reasons that I like this area so much is it's kind of a perfect space for both researchers and engineers to work together. Researchers can kind of work on better ways to do SNARKs, better, more efficient, more expressive, more properties. And engineers basically need to build the tool chain that makes SNARK usable. So it's kind of an area. There aren't too many areas like this where researchers and engineers sort of work hand in hand, and kind of ideas from the research community very quickly make it into the tool chains and get adopted into real frameworks and then adopted by the companies listed here. So in that sense, there are not too many areas that have such a rapid progress and such a strong collaboration between research and engineers, and basically anybody can contribute. If you're a developer, you have a lot to contribute. If you're a mathematician, you have a lot to contribute. So it's kind of a very broad area where everybody gets to contribute, and also it's a very welcoming community. So I hope to see more of you in this space. So before we jump into LatticeFold, I wanted to just give a few examples of applications of SNARKs that I kind of find amusing. Hopefully you'll find them amusing too. So one is kind of a recent paper that we wrote. This is with my students, Evan Laufer and Alex Ozdemir, appeared in the last CCS, which is basically a way to generate a zero-knowledge proof of knowledge of a lean proof. Yeah. So I don't know if you guys have heard of lean, but lean is basically a language that allows you to express proofs. Yeah, mathematical proofs, proofs of even correctness of software, and so on. So just to map it to our previous terminology, the public statement X would be a theorem written in lean. The witness would be a proof for that theorem also written in lean. And the circuit that we're trying to evaluate, the prover is trying to prove that it knows a W for this X such that C of XW is equal to 0, where the circuit is basically the lean verifier. Namely, the circuit is 0 if and only if the lean verifier will accept the witness W as a valid proof for the statement X. So again, we can use this to prove knowledge of a proof of a mathematical theorem. We can also use it to prove knowledge of a proof that a particular piece of software satisfies a specification. Yeah, and this is a zero-knowledge proof, so you don't reveal anything else about the software other than the fact that it satisfies a specification. Yeah, this is kind of why we got interested in this. But there's kind of a funny mathematical story here, which is basically, so the system called ZK-Pi, yeah, it's a SNARK system for proving that we have lean knowledge of, it's a ZK-Pi is a proof system that outputs succinct proofs that prove knowledge of a lean proof. So the proof, as we said, is quite short. It's kind of it's independent of the length of the actual proof that is presented to ZK-Pi. And so the reason I find this amusing, the reason I wanted to tell you about this is this is the sort of thing that Fermat would have found very useful. So Fermat didn't have space in the margins of his notebook to write his proof for Fermat's last theorem. Well, he could have actually used ZK-Pi to generate a succinct proof. The proof hopefully would fit in his margins, and that would have convinced us that he actually knew a proof. The other way to think about this is, if you think of some of the hard math problems these days, like, I don't know, the Riemann hypothesis, for example, proving the Riemann hypothesis. It's quite possible, maybe even likely, that the Riemann hypothesis will be proved this century by a machine learning algorithm. But the machine learning algorithm will generate some sort of a billion-page proof that no human would understand. So maybe we'll have a proof, we'll be convinced the Riemann hypothesis is true, but nobody will understand it. The cute thing about ZK-Pi is you can take this billion-page proof of the Riemann hypothesis, convert it and compress it into a SNARK, and then you can print a proof on your T-shirt, and you'll have like a proof of the Riemann hypothesis on your T-shirt. Maybe that's kind of a dream that we'll get to one day. What's interesting about that little short string that proves the Riemann hypothesis is it says basically either the Riemann hypothesis is true, or the SNARK that we're using is not sound. Yeah, so maybe let's say we're using a SNARK that depends on some hash function. So it would say that SHA-256 is not a good hash function. Yeah, so you prove one of those two facts using a SNARK. What ZK-Pi can currently do is it can generate proofs for much of the standard library of lean. And lean also has MATLib, which encodes much of mathematics. So all the standard proofs of mathematics are encoded or many of them are encoded in MATLib. And we can handle about 11% of those theorems, generate SNARK proofs for those proofs. The reason we can't do more is because MATLib uses some features of Lean 4 that we don't support. So if anybody wants to kind of build a full snark proof or full lean proofs, that would be really cool. And maybe we can do, we can generate snarks for all of MATLAB, which would be kind of entertaining because some of the proofs in MATLAB are actually quite long, and snarks would let us generate short proofs independent of the length of the proof. So that's one example. The other example I wanted to very briefly mention is in the context of machine learning and AI. So this is, again, work that we did with 2 students and a colleague at UCSD. It appeared at one of the ML conferences in ICLR. And so this is called fair proof. What it does is it proves that a machine learning model actually is fair. So let me explain the problem to you. Again, I'm going to go through this pretty quickly. It's kind of a cute story, but it says that suppose a bank wants to train a secret machine learning model that will decide whether customers get a mortgage or not. Yeah, so it builds a model with parameters theta. It's going to commit to this model theta, so the customer will have the commitment. And now it's going to evaluate, it's going to use this model to decide to make mortgage decisions. So why does it want to commit? Well, one thing that we would like to make sure is that the same model is used for all clients. It's not that one model is used for me and a different model is used for you. It's like the bank is committing to using the same model for everybody out of fairness. But then in addition, we want to make sure the model itself is fair. In other words, it doesn't use sort of disallowed characteristics. Yeah, for example, it doesn't discriminate based on gender or name or whatever other characteristics we don't want to discriminate on. And so we're going to prove that the model is fair in zero knowledge. Yeah, so let me explain how this works. So basically now Alice will send her financial data to the model. The model will send a response back saying, you know, you're approved or you're not approved. But in addition, what will come back is a proof pi. And what this proof proves is, first of all, that the committed model was used to make the decision on Alice's application. So it's one global model that's used on everybody. And then the other thing it will prove is that the model satisfies this property called local individual fairness. This is a property from the algorithmic fairness community, which basically says that, you know, treating similar people similarly. So if you and I differ on only one feature, one characteristic, then the model will decide the same way for both of us. Yeah, so what this proof does is it basically looks at Alice's input, it kind of draws a box around the input, and it proves that the model will output the same output for all points in that box. Yeah, so similar people are treated similarly. Yeah, and so this was kind of a fun, nice application of ZK proofs to prove not only was the model evaluated correctly relative to the commitment, but the model also is fair in the sense that all the points around for all the points around the given point, the model outputs the same result. Yeah, so this was kind of a fun project to do. Okay, so good. So again, I have one more thing I wanted to do before we go to LatticeFold, and that is I wanted to mention kind of a cute open problem. So I gave this talk to the fully homomorphic encryption people, and so I wanted to just tell them about kind of an interesting open question in the SNARK world. So this is kind of a question at the intersection of SNARKs and FHE. So let me explain the problem, and maybe I can get you excited about this question. So the problem has to do with what we call collaborative proof generation. Collaborative proof generation. Yeah. The problem is this. Suppose we want to generate a proof, pi, yeah, one of these succinct SNARK proofs, but the witness for the proof is actually distributed. So not everybody, it's not the case that one entity knows the witness itself is distributed across multiple parties. Now this comes up in a lot of different cases. Most often it comes up in gaming, where, you know, if we play a multiplayer game, because of the fog of war, nobody knows the full state of the game. Like, you know, one player knows their state, another player knows their state, a third player knows their state, and so on. And what they'd like to do is they'd like to prove that the three of them would like to prove together that a particular state transition for the game, you know, if somebody makes a move, they'd like together prove that the move was actually processed correctly. Yeah, so that's an example where the witness is shared across three parties, and together they want to generate a proof. This comes up also in the world of finance, where you might imagine, you know, different banks see different views of the global transaction graphs, right? So one bank will see the state of the graph relative to their customers, another bank will see the state of the graph relative to their customers, and together they'd like to generate a proof that there's no money laundering in the entire financial system. Yeah, that's another example of a collaborative proof. Yeah. And so how do we do it? Yeah, so actually this is what I wrote here. So we have our witnesses split across the parties, and together they basically like to generate a proof that the combined witness causes the circuit to be zero. Yeah, so as I said, this comes up in a bunch of applications, and so the question is how to do it. So yeah, so we did some work on this. We call it collaborative ZK SNARKs, and so let me explain kind of the options for doing it. So the first trivial option, which is kind of getting some popularity these days, but it's kind of the easy option, is basically to use a trusted execution environment, right? The way this would work is basically the trusted execution environment is going to have a secret key. Everybody will send their encrypted witness to the TE encrypted under the TE's public key. The TE will run the prover, the SNARK prover inside of the TE, and then it will output the proof and destroy its state. Yeah, so now this way we get the proof and nothing else. One thing that's interesting about this is SNARKs these days use GPUs, so SNARK provers use GPUs, and so what we will need for this is actually a TE that has the ability to use GPUs inside of it. So up until recently, we didn't quite know how to do that. It's just recently that NVIDIA released the H100, which has a TE built into it. But even that's not enough because these SNARK provers often use multiple GPUs. And so we would need a TE that sort of clusters around multiple GPUs. And that actually turns out that's not quite well supported yet. So, you know, there's more work to do to actually make this vision true, even from a systems point of view. Okay, so that's one solution. We want a cryptographic solution. We don't want something that depends just on hardware. So the second option is basically to run the SNARK prover inside of a multi-party computation. Yeah, so we do this big multi-party computation between the three witness holders, and out comes the proof. Yeah. Now here, this is kind of the, so basically what this says is we need a SNARK prover that's friendly to MPC protocols. Yeah, so this is kind of a new requirement on SNARKs. How do we build MPC-friendly SNARK provers? And it turns out that's actually exactly what we looked at in the original paper back in 22. And surprisingly, I have to say, I won't dwell on this too much. I will tell you, this is a very strange situation where MPC does not add much overhead to the SNARK proving process. Yeah, and this is because the bulk of SNARK proving has to do with multiscalar multiplication. It has to do with FFTs. These are sort of all linear operations. And so they can all be done very efficiently when the data is shared using a linear secret sharing scheme. Yeah, it requires no communication. So what these graphs are showing is basically that the MPC, that running the SNARK in an MPC doesn't add much overhead over running the SNARK on a single server. So that was kind of surprising. There's a lot more work on this. I kind of cited some of the papers. There's many others. So it's really quite interesting to get collaborative SNARKs to run as fast as possible using an MPC. And there's even a fantastic company called Taseo. I really love what these guys are doing. That is, this company is really kind of commercializing running collaborative SNARKs using MPCs. But there's a third approach. The third approach is basically to use FHE, right? So here, what's interesting is we can use what's called threshold FHE, where really, again, the server will publish an FHE public key, a fully homomorphic encryption public key. The provers will send their witnesses encrypted under the FHE public key. The prover will run the SNARK prover inside of the FHE. This is a bit difficult for the prover, but let's dream. And then basically what will come back will be the encrypted proof. And now the provers will individually, this is using threshold FHE, so then these provers will individually threshold decrypt the encrypted proof, and the proof comes out. Okay, so this is basically just one round of interaction. The clients, you notice they do very little work. All they do is they encrypt their view of the witness, and then they decrypt the final proof. So they do very little work. It's only one round of interaction, and the proof comes out. One thing that's interesting to think about is this FHE server, this big server, actually could cheat. It could actually run an incorrect version of the proving circuit. Yeah. And so if that happens, it would send, what would come back would be an incorrect version of the proof. And then the server can observe to see whether the final proof was output or not. And maybe that leaks information about the witnesses. Yeah. So basically, each run of this protocol might leak one bit of information about the weaknesses, which is not good. So maybe we actually have to layer a snark on top of the FHE, but hopefully there are more efficient ways to do it. Yeah, so the goal is basically now to build an FHE that efficiently supports snark proving. So even on this, there's some initial work. I kind of wrote two very recent papers on this topic. I think there's a lot more to do in this area. What's kind of interesting is this 2024 paper. It's kind of, I'll just quote what they're saying. You should probably read the paper for yourself to be convinced. But they're saying basically that without FHE, client computation took 10 minutes. They were able to reduce it to a few seconds. The server computation was only 20 minutes, and they were able to generate the snark proof. Yeah, and so this is in some sense a way to use FHE to offload proof generation. But again, you should read the paper yourself to be convinced whether of these numbers. So the question is, I'll go back to collaborative snarks. The question is, can we do collaborative snarks more efficiently or at all using FHE? I think that's a really interesting question, and hopefully some of you will be excited enough to go explore this. Yeah, so hopefully there'll be more papers on this soon. Okay, so with that, I'm going to turn to LatticeFold. Yeah, so what we're going to talk about is basically how do we use lattices to build snarks. So in some sense, we have pairing-based snarks that are quite popular and actually generate quite short proofs. We have code-based snarks like SNARKs and others, and Blaze and many others. Those have their own properties, and we also have lattice-based snarks. Lattice-based snarks have not been as widely explored, and probably that's an area where there's a lot more work to do. So we wanted to explore basically how do we use lattices for folding. And so let's talk about how this works. So first of all, I have to start with pre versus post quantum snarks. So let me remind you that snarks only have this property called computational soundness. Yeah, they're only secure as long as the underlying complexity assumption used to build the snark holds. In particular, if the assumption breaks, then it turns out we can actually prove false statements. Yeah, so for example, if SHA-256 happens to not be collision resistant, then yeah, SNARKs would have a problem. If discrete log happens to be easy in certain groups, then pairing-based SNARKs would have a problem. Yeah, they would allow you to prove false statements, which is really kind of the worst possible type of failure for a SNARK. Well, so we have a lot of pre-quantum SNARKs. They're really quite great. I wrote down a few of those here. There's lots of them. The proof size is really short. The verifier time is really fast. So these are all really fantastic SNARKs. The problem, of course, if there's a quantum computer, these are pairing-based SNARKs. If there's a quantum computer, it will break those SNARKs, and the prover will be able to prove false statements. We also have post-quantum SNARKs. These are hash-based or lattice-based. So these are supposed to be secure even if the adversary has a quantum computer. The problem with these is the proof now all of a sudden is much larger. Concretely, it's on the order of 50 kilobytes. And in some of those, also the verifier runs in quite a bit of time. I just quoted numbers, for example, for Greyhound, which is a lattice-based SNARK. You can compare it to a pairing-based SNARK. Of course, code-based SNARKs actually do have faster verifiers, but regardless, they still have large proofs. Yeah, so in some sense, there's a gap between pre-quantum SNARKs and post-quantum SNARKs. So so what I want to do now is basically kind of separate into two types of SNARKs, right? So on the one hand, we have kind of what we've been talking about so far, which is what I call monolithic SNARKs, where the entire statement is proved at once. Yeah, so you give me some large computation, like, I don't know, proving that a certain machine learning model is fair, and we do that entire SNARK in one monolithic proof. Yeah, so the problem with those SNARKs is they end up eating up a lot of memory. Sometimes they generate larger proofs. And in fact, in practice, this is not what's used. Yeah, if the statement is too large, often we just run out of memory, and we need SNARK systems that just are, have that have better memory efficiency. So the other way to build a SNARK is to use what I call a piecemeal SNARK. So what a piecemeal SNARK does, the technical names for these are IVC, PCD, SNARK recursion. Yeah, I like to be honest, I like the term piecemeal SNARKs. I hope this catches on because it's very descriptive. So what we do in a piecemeal SNARK is we take a very large statement that we're trying to prove, we break it up into small steps, and then we prove each step on its own, and then we do a proof of proofs to prove that all the steps are correct. Yeah, so because each step in this piecemeal snark proves a very small statement, the amount of memory that we need is very low. So this actually can be used to prove very, very large statements. We just do them in a piecemeal fashion. So overall memory usage is quite low, and we also get relatively shorter proofs. Okay, so the main point that I want to make in this talk is that SNARKs that lattices are not great for monolithic SNARKs, but it turns out lattices are fantastic for these piecemeal SNARKs. In particular, lattices are really good for folding schemes. Yeah, and that's kind of what I want to make, the point I want to make. And I think there's a lot more work to do here. Okay, so let's kind of remind ourselves how these piecemeal SNARKs work. So this dates back to the ideas of Valiant back in 2008. And so what we do is, again, we break our computation into a sequence of small steps. So you can see here, F is our small computation, and we just repeat F over and over and over again, potentially with different inputs. In this case, I guess we're verifying transactions. So each F will verify one transaction, and we can verify like 1 million transactions in this way, just doing it one step at a time. So the memory usage is not very high. The way this works is basically every step of the snark is going to verify that the function F is evaluated correctly, and it's also going to verify that the proof on the previous steps is also valid. So the inputs to our circuit is going to be the basically the state from the previous invocations of F, along with a proof that all the previous invocations were done correctly. And then we generate a new proof that now we started with a proof of I-2 steps. Now we generate a proof of I-1 steps. And so on and so forth. And so eventually we end up with a proof of all the steps that we wanted. And that final proof convinces the verifier that, in fact, all the steps since the beginning of time until the very end were all executed correctly. Effectively, this is a recursive snark because at step I, we verify the proof at step I-1 and also prove that the latest invocation of F was run correctly. Yeah, so in some sense, you almost think of this as a kind of a proof by induction. Yeah, we prove that the first I- steps were done correctly. We prove that the I step is done correctly, and that proves that all the first I+1 steps were done correctly. Okay, the problem with this, I should say, the benefits are small memory footprints. It's great. You build a proof in a stream, so the transactions can be revealed one at a time. They don't all have to be revealed at the beginning of time, and it can also be parallelized using a tree. So this is great. The problem, of course, is you have to expand your circuit with the SNARK verifier. This is pretty expensive. The SNARK verifier could be quite complicated to implement inside of a circuit. And you have to also do complicated proof generation. At every step, the prover has to generate a full proof, which is then fed into the next step. Yeah, so both the expansion of the circuit that's being proved and the fact that we have to generate a full proof really slows this process down. So the better mechanism is what's called folding. Yeah, so again, hopefully many of you have heard of folding. And so again, the way folding works is typically we're going to use a commitment scheme. We're going to commit to the witness using a commitment scheme. We're going to treat the witness as a vector. We're going to have a short commitment to this vector where we're going to use linearly homomorphic commitments. Yeah, so given two witnesses, basically the commitment to their sum is simply the product of the commitments. Yeah, so these are called linearly homomorphic commitments, although I should say that there's really elegant work, recent work, it's called ARC. Here I linked to it over here, that actually builds a folding scheme from commitment schemes that are not homomorphic. So this allows us to use Merkle trees, for example, for commitments. In particular, it fits very well with code-based SNARKs. And allows us to do folding even on code-based SNARKs where we don't have homomorphic commitments. But in this talk, I'm going to focus on homomorphic commitments. And so the way folding works is the first thing what we do is we expand the statement, the relation that we're proving by including a commitment to the witness along with the public input. Yeah, so you can see the public statement that will be given to the verifier is now X plus a commitment to the witness. And what we prove is that the prover knows W and the prover knows W, such as XW is in the relation, and CW is a commitment to W. This is just a mechanical expansion that we have to do to apply folding. Now, what folding does is basically it takes two statement witness pairs, so U1, W1, U2, W2. These are two statement witness pairs, and it reduces them to one statement instance. To one statement and witness, along with a proof that this folding was done correctly. Then there's a folding verifier that takes the compressed instance along with the original instances and the proof, and then decides whether the folding was done correctly or not. Yeah, so this is kind of how folding works. Yeah, we take two witnesses and sort of compress them into one, two statements and compress them into one, and then the verifier just checks that this compression was done correctly. And there are some properties that folding has to satisfy. Of course, if the prover is honest, the verifier should always accept. And then it has this property. It's a very beautiful property called the reduction of knowledge. I really like this paper to introduce this notion of reduction of knowledge that says if U tilde and W tilde are actually in the relation, in other words, U tilde, W tilde are valid, then and the folding verifier accepted the folding proof, that means that actually the prover knows witnesses for the original instances. Okay, so basically if the folded instance is in the relation, then the original instances must also be in the relation, and in particular, the prover will know witnesses for those instances. Okay, so that's what folding allows us to do. It takes two instances, combine it into one. If we can prove that this combined instance is in the relation, the original instances must also be in the relation. Okay, and it turns out the benefits of this is that folding is much faster than generating a complete proof, and verifying is much faster than verifying a complete proof. Yeah, so this is kind of a win on both objections we had to the basic recursive method. Okay, so now how do we build piecemeal SNARKs for folding? Well, it's actually quite simple. What we'll do is we'll basically have an accumulator statement that keeps accumulating or keeps folding statements into an accumulated statement. Okay, so again, what we have is, we have a folded statement coming in that is the folding of the first I minus 2 statements. We have a new statement that comes in, which is the verification of the current transaction. We fold those two into a single statement that now proves that all the first I minus 1 transactions are correct, along with a folding proof. And then what the relation does is basically it verifies that the function f was done correctly, and it verifies that folding was done correctly. Yeah, so that the folding proof actually satisfies. So these are kind of the inputs to the circuit. And what comes out of this is basically a folded statement, which we can keep on applying recursively. So the way to think of it is we have this accumulator coming in, and we keep folding more and more statements into this accumulator until at the very end, what pops out is an accumulated statement, and then we just have to give a regular proof, cross 16 or whatever, that or SNARKs, whatever, that the final folding statement is correct. Yeah, and so this kind of is a very elegant way to do piecemeal SNARKs, using a very fast folding prover and a very fast folding verifier. Okay, so that's kind of the idea of folding, and the question is just how to implement it. Okay, so first of all, we need to use a homomorphic commitment scheme. So which homomorphic commitment scheme should we use? Well, the first folding schemes use the classic homomorphic commitment scheme, namely Pedersen commitments. So the way Pedersen commitments work is they take a vector of length n, and they commit to it by doing multiscalar multiplication. Yeah, they put the vector in the exponent and do all these products. Yeah, this goes, if we use an elliptic curve, this basically, even though we're committing to a vector over fp, the result is an elliptic curve point, which is a pair of values defined over fq. Okay, so the curve itself has size p, but it's defined modulo q. So we start the witness would be a vector mod p, but we end up with a pair of points mod q. So this is great. So the nice thing about using Pedersen commitment is we get very clean proof of soundness that folding is correct. So this works really well, but there are some problems. The first problem is we have to work with relatively large fields. We need discrete log to be hard, and so for discrete log to be hard, we need our field FP and FQ to be quite large. Particularly, they have to be at least 256 bits long. The other problem is that the folding verifier uses both operations in the group on the elliptic curve, and it uses operations on the finite field. Since the curve is defined over FQ and the finite field is FP, that means that our circuit has to support operations both mod P and mod Q. But a circuit can only support operations modulo 1 prime, and this means we have to do field emulation. For example, we have to implement arithmetic mod FQ using FP. Yeah, and again, that introduces quite a bit of complexity into the circuits, in particular into the folding verifier circuits. Yeah, so there's there's a bunch of overhead basically in making this work. And finally, Pedersen commitments are based on discrete log, so they're not binding if the adversary has a quantum computer, which again will allow the prover to produce proofs for false statements. So what we would like to do is we would like to do the same thing using lattices. The question is, so the goal would be, we started with the goal of building something that's post-quantum secure, but it turns out lattices have other benefits. And so, yeah, we show that we can do this using a lattice homomorphic commitment. Unfortunately, there are lots of complications. Yeah, and I want to walk you through the complications, and then we'll end. First of all, let me say that the point of doing folding using a lattice-based homomorphic commitments is A, we can use much smaller fields, only 64-bit fields, so they fit in the word of a computer. In particular, the hash function we're going to use is called an itai hash, which is dramatically faster than a Pedersen hash. So that's great. Potentially, we can also, it turns out the rings we will be using are the same rings that are used in FHE, and the FHE community is spending a lot of effort now to build hardware to accelerate FHE operations. The same hardware, it turns out, can also be used to accelerate folding for LatticeFold. Yeah. So it's really quite remarkable that potentially there's massive opportunities for hardware acceleration using the hardware that's being built for FHE. Finally, as I said, fold.v uses arithmetic in only one field, so there's no need for field emulation. And as we said, this was our original motivation that it be post-quantum, but then it turns out it has all these other benefits as well. Okay, so let's see how this works. The first thing I have to explain is how does itai commitments work. And so the way itai commitments work is actually very, very natural. Basically, we start with the 64-bit prime Q. We define our noise-bound beta, which I'll define this to be 2 to the 16 in this case, so much, much smaller than Q. And I'm going to assume that the dimension of the vectors we're using are larger than the security parameter. Now, for a vector, so for a low norm vector over FQ, yeah, you notice this is an n-dimensional vector, but all the elements of the vector are small. They're much smaller than Q. The way we commit is basically we fix a random matrix A, and then we commit by simply computing A times W. So we take a long low norm vector, and we map it into a short random vector in ZQ to the lambda. Okay, so this is a compressing hash function. And it turns out it's actually binding, it's collision resistant, as long as the vector W happens to be low norm. In other words, you cannot find, or at least we believe that you cannot find two low norm vectors that happen to map to the same commitment value under a fixed random matrix A. Okay, and this scheme, of course, this hash function, of course, is trivially homomorphic because all we're doing is a matrix vector product. So yeah, it's clearly additively homomorphic. So as I described it here, this matrix vector product is somewhat slow. It takes lambda times n ZQ operations in order to commit. It turns out we can speed this up by not using ZQ, not using integers, but rather using rings or modules. Yeah. So what we'll actually end up using is the ring ZQ modulo some polynomial, where d usually is a power of 2. Yeah. So we're working in this ring. And now, given a lower norm vector, what we'll do is, again, we'll do A times W. Yeah, so here, so we're taking a vector of, this is a bit inaccurate, sorry. This is a lower norm vector in RQ. Our matrix is, this is what we started with integers. What we're going to move to is now we're going to commit to vectors defined over the ring. Yeah, so instead of committing to integer vectors or vectors over our finite field, we're going to commit to vectors over our ring, where now, because we're working with a d-dimensional ring, everything compresses by a factor of d. Yeah, so our matrix compresses by a factor of d, both in width and height. Our vector compresses by a factor of d. And so now this matrix vector product is both in height and in width, compressed by a factor of d. So this will only take lambda n over d squared operations in RQ, but operations in RQ can be made quite fast using an FFT. And so overall, this is like a factor of d acceleration over using direct fields. Yeah. So this is why we like to work with rings. Basically, the itai hash is much faster when we do that. But again, I want you to remember the difficult challenge is that this is only binding, this is only collision resistance when all the coefficients of this vector w hat happen to be small, happen to be in some small interval. So that's the problem. So the question then is, how do we fold? How do we do folding using itai? And immediately we run into a problem. So the way folding typically works is, again, we have our commitment to the witness and we have the witness. The way folding works is we're going to choose a random gamma, and we're going to take linear combinations of the commitment to the witness and the witness itself. The problem is, once we start taking linear combinations, the witness is no longer low norm. Yeah, and so we kind of exceed our norm bounds. And as a result, the system will stop being sound because now it's not, the itai hash is no longer binding. Yeah, so this is a problem. Yeah, so we have to kind of deal with the fact that the scheme is binding only for lower norm vectors. So what do we do? What do we do? How do we address this? Well, so the first idea in LatticeFold is to say, well, let's not fold directly. So we're given two instances and we want to fold them. We're not going to fold them directly. Instead, what we're going to do is we're going to take our witness vector and we're going to split it. We're going to do some decomposition on it. So we're going to do, basically write it base B. Yeah, so we take our element A, for example, we write it base B, and then we're guaranteed that all these A1 to AK are actually small numbers. More generally, what we'll do is we'll take our witness and also the commitment to that witness, and we'll split it up into commitments and witnesses where, I guess here I split it up into two parts, where each part is now only as big as square root of beta, yeah? So before these elements were as big as beta, now each part we split it up. So now we have two commitments and two witnesses, but the point is these are lower norm. Their norm is only as big as square root of beta. We're going to do the same thing to the second commitment and the second witness. Okay, so now we have 4 commitments and 4 witnesses, and essentially what we do is we do a 4-way fold. Yeah, so we fold all these 4 into one statement and one witness. And the point is that when we use these coefficients, gamma 1, gamma 2, gamma 3, gamma 4, to do the folding, we're going to use relatively low norm values of gamma, such that when we combine these w's, the combined w stays lower norm. So w tilde here will remain as a lower norm vector, and that would allow us to commit to it using the itai commitment. Yeah, so this ensures that w tilde stays lower norm, and as a result, the folding is still sound. Okay, so the way LatticeFold works is rather than folding directly, it does decomposition and then folding. Unfortunately, this is not enough. Yeah, so let me explain. This just doesn't work. This is still insecure. Yeah, it's kind of interesting. This splitting by itself is not enough. So the second challenge we have to deal with is how do we make sure that this folding scheme is a reduction of knowledge? In other words, how do we make sure that if the prover has a witness for the folded witness, it should also have a witness for the original statements? So so the problem is that really the malicious prover can come up with whatever witness it wants for this folding statement. In particular, what we need to do is argue that not only does the prover P star know witnesses for the original statements, those witnesses also have to be low norm. Yeah, it's not enough for the prover to just know witnesses for the original statements. They have to be low norm, otherwise the itai hash isn't a binding commitment to those witnesses. Yeah, and again, if you just do what I just said on the previous slide, you end up with an insecure folding scheme. So yeah, so here I kind of explained the problem in a bit more detail, that if you just try to apply the standard extraction method, you end up having to divide by some value. This value, basically dividing by this value, blows up the norm of the witnesses, and as a result, the witnesses we end up with will have too high norm, so we wouldn't have an extractor, and in fact the scheme would be insecure. So the hardest part of LatticeFold is that in the folding circuit, we also have to prove that the input witnesses themselves are low norm. Yeah, this was kind of the most challenging parts, and this will basically ensure that the original commitments to those witnesses, in fact, are binding commitments. Yeah, and so what we do is effectively most of the work in LatticeFold is basically what we call a range proof on the, it's a lattice-based range proof on the incoming witnesses to prove that they're sufficiently small, and we do this range proof using a sum check. So that turned out to be quite cute. So yeah, so I think overall the construction is really kind of pretty. Basically, what happens is the witnesses come in, the prover does a range proof on the witnesses. We do the composition, we do the decomposition of them into smaller witnesses. Then we do the folding, folding that preserves norms, and we end up with a secure folding scheme. Yeah, so basically in the paper, we give a proof that this is in fact a secure folding scheme. Yeah, so this is kind of a high-level description of how LatticeFold works. I just wanted to show you that folding using lattices is quite promising for all the reasons we discussed before. Small fields, we have very efficient verifier circuits, it's post-quantum, and to me what's exciting, honestly, is we might be able to leverage the same hardware acceleration that's being used to develop FHE, that would all of a sudden be used to also generate SNARKs very quickly. Yeah, so to me, that's kind of exciting. It turns out this can generalize. We can support high degree constraints. This is what's called CCS. I'm not going to describe that over here, but you can see it in the paper. Okay, so this is basically all I wanted to say. And so let me conclude here. If you're interested in looking at the paper, I have a link to the paper here. Hopefully, this short overview is clear, maybe gets you excited in using lattices to build SNARKs, and hopefully we'll see much more in this direction. Okay, so I'll stop here, and I'm happy to take any questions. Thank you very much for...
Thank you so much. Also, just a note for everybody that is watching, we will be in touch with Dan to provide you a copy of the slides. And as I said, a recording will be made available in the next 24 hours. And you can look at it, and we will make sure to provide it within the Hacker Pack, as we shared in the chat section. Now, Dan, there's been a few questions that came in. You can have a look at them in the questions section on the bottom right side next to the chat one. And feel free to respond to them one by one. Ideally, read out the question as well, so that the people that are watching the recording can get the context of the response.
Let's see, I'm looking through the questions. I see, so people are excited about BLS. Okay, I could have talked about BLS. Wait, there are no questions.
Please click on the questions tab. There's like a question mark.
Oh, it's a separate tab. Oh, there's separate questions. Ah, I see.
Yeah.
Oh, okay, I see. Okay, so Daniel has a good question. Why do we use ITI commitments as opposed to any other lattice-based commitment scheme? Okay, so that's a very good question. So the ITI commitments are quite simple and efficient. They're also linearly homomorphic. Yeah, so we need linearly homomorphic commitments. It turns out there are other linearly homomorphic commitment schemes from lattices. In fact, there are some that even remove the requirement on the norm bound that we had to struggle so much with. It turns out they are far less efficient than ITI, and the scheme that we end up with is much more complicated than LatticeFold. But to be honest, this is a fantastic area of research. If you can think of another commitment scheme that's linearly homomorphic, and ideally the property would be that it would be binding even if the vector was not low norm, the input vector was not low norm, that would dramatically simplify lattice folding. Yeah, so I highly encourage you to think about that. That's really quite interesting. The other direction that might be interesting to look at is, I mentioned this ARC paper, ARC, which I really like. It's a folding scheme using non-linearly homomorphic commitments. And maybe that could be used also to speed up lattices by using a non-linearly homomorphic lattice-based commitment scheme. So this is another area to explore, and yeah, it's quite interesting. There's lots to do here. Okay, so let's see. Lee's asking if the ring-based ITI is still as secure as the integer-based one. Oh boy, that's a great question. So as far as we know, yes, but now you ask, well, what can we prove? And it turns out the hardness proofs for integer-based lattices are in some sense more convincing than hardness proofs for ring-based lattices. Yeah, I don't want to get into the technical details of why I say that. It has to do with what the random self-reductions are over, but that shouldn't deter you. Yeah, as far as we know, ring-based lattice problems are chosen properly, parameterized properly, are just as secure as lattice-based ones. Yeah, so as far as we know, in fact, all of the NIST standards are all ring-based because of the performance benefits. Let's see. What are the fundamentals? So Sebastian asks an interesting question. What are the fundamentals to not being QP, like SHA-256, versus some lattice-based signatures? Quantum proof, I guess. QP is quantum proof, yeah? I would say post-quantum. PQ is typically the word. Post-quantum. Yeah, okay. So I think what you're asking, Sebastian, is a really good question, which is what do we believe is more likely to be post-quantum? Do we believe SHA-256, collision resistance of SHA-256 is more post-quantum, or is ring-based lattices more likely to be post-quantum? I think everybody would agree that collision-resistant hashing is kind of more safe, yeah, because we have many options for building collision-resistant hashes, whereas lattices, we have to just use lattices. If it turns out for some reason that lattices are not post-quantum, then we have a problem. Whereas if SHA-256 is not post-quantum, we'll just use another collision-resistant hash. The problem is that, of course, lattices have much more algebraic structure than simply collision-resistant hashing. And as a result, we can use lattices to build many things that we can't just do using hashing. Yeah, and so that's why we like to use them. One would suspect that the algebraic structure of lattices should allow us to build much better SNARKs. Yeah, and in some sense, that's what LatticeFold is trying to do. So folding in particular is easier with lattices than it is with hash functions. In that the hope is that we would get good schemes from that. Yeah. So this is why LatticeFold is post-quantum. It's potentially much more efficient than doing folding using a code-based SNARKs. Let's see, Sebastian, you're asking other questions. Why some schemes are post-quantum and others are not? Oh, okay. Well, for example, if you have a quantum computer, then discrete log is easy, and therefore all the pairing-based schemes would not be secure because fundamentally Peterson commitments are not secure if you have a quantum computer. So that's that. Let's see. So Manish is asking a really good question. How does the accumulator grow over subsequent folds? Does the folding function get slower over time? Yes, that's a really nice question. Turns out, no. Actually, the accumulator does not grow, and the folding function does not get slower. You accumulate, but because you're just accumulating by doing random linear combinations, everything stays the same size. Yeah, so it's really quite interesting. What you could say, though, is that security degrades with the amount of folding. Yeah, so you have to make sure your parameters are sufficiently high to address the amount of folding you want to do. But the relation is actually quite friendly. So the parameters are not going to grow by that much, even if you need to fold quite a bit. So yeah, it's really quite a powerful mechanism. Yeah. I think I answered all the questions.
Yeah, Hasib is saying he has 3 questions coming in, but he's trying.
Oh, right. I see that. Mike is asking, what do I mean by norm? Yeah, so norm is over integers. It would just be the L2 norm, and in the ring, it would be the norm of the coefficients. Exactly, the coefficients of the polynomials. Thank you, Mike. That's a good question. I see. They go. I need to go from top to bottom. Got you. Okay, let me start with Hasib's question here. I see. So Hasib is asking about bilinear pairings are complex. You know, I actually tend to disagree with that. I think pairings are actually, if you treat pairings as a black box, in other words, you just think of them as a bilinear map from two groups to another group, then pairings are actually quite simple. Yeah, and in fact, all of the SNARK constructions use pairings as a black box. You don't need to understand how pairings actually work. Just treat them as a black box, and then the construction should be not too difficult to follow. So, yeah, I think I would actually suggest starting with that. The code-based SNARKs are also quite elegant. Actually, maybe I should say, if you are interested, Hasib, I just posted 2 lectures on code-based SNARKs, which start from 0 all the way to how the SNARKs work. So this is in the Zero Knowledge Whiteboard sessions. This is Anna Rose's Zero Knowledge Whiteboard sessions. If you just search for ZK Whiteboard and my name, you'll find those lectures, and they're very accessible to someone with a bachelor's degree. That's what they're designed for. So hopefully those will be useful for you as well. Let's see. Second question. What are some of the books or papers that allow an intermediate level developer to do a deeper dive into SNARKs and bilinear pairings? I see. So here I would point to Justin Taylor's book. So Justin Taylor has his book on SNARKs, also starts from basics and takes you through how they work. So that's probably a good resource, and I would start with that. And there's a third question. It's just two questions. Okay, got it. All right. Thank you very much. Oh yeah, and any great resource to dive into this field related to SNARKs and FHE. I see. So maybe my talk was a bit too low level. You know, so Sebastian, if you're looking for a simple lecture to take you through this, you know, it's interesting. So we did a blockchain week at Bar-Ilan University. If I post a link, will they be able to see it? Yes.
Yes.
Let me see if I can quickly find it. 1 second. Yeah. Yep. Okay, so here, let me just post how do I post a link?
You can do so in the chat section.
Oh, I see. Okay. So here is a link. Right. So this link basically points to a mini course on blockchains, and the second day of that mini course was just about SNARKs. So I think that's kind of also an introduction that goes from 0 to how SNARKs work. So I would say that that's a nice resource, just 2 lectures. If you want another resource, we have this course called ZK Learning. So ZK Learning, let me post a link to that. So that is another good resource. Yeah, you can kind of look at some of the lectures there. Hopefully those will be useful to you. And yeah, hopefully that works. Cool. Looks like we did it all.
Yes, thank you all for thank you for sharing those links. Those have been really useful. A lot of bootcamp participants have been asking for additional reading materials, so these I think will fit right in, and they will be a great study and learning material for the majority of them. Thank you so much. There's been a lot of questions. I think this was really engaging. I think the level was, like, contrary to what you might think I think is quite accessible, and it's going to surely be well received among everybody that did not manage to make it. As I said, this lecture will be recorded and will be made available to everyone. And for any follow-up questions, please make sure to post either on our Discord or also on the Polyhedra Discord. They have a dedicated bootcamp channel where you can post any technical questions as follow-ups. Regarding the slides, we will be in touch with Dan and hopefully provide these slides as soon as possible and add it to the Hackerpack as all the previous ones. Thank you so much, Zan. This was a great lecture. For everybody else, just wanted to make just want to remind you we have 2 more workshops coming in tomorrow. We'll start off with Justin Drake in the morning, and then we'll continue on with Abby Shalat from Google. So another exciting day tomorrow. I hope you enjoyed the workshops today, and there will be a lot more to come. Thank you for your time, Dan. This was amazing. Have a great day, everyone.